Hi everyone, welcome to this video. My name is Afsana Mamadova. In this video, we will talk about Raft. Raft is a consensus algorithm, and by the end of this video, you'll be able to understand it and explain it to others. So let's get started. Imagine you have 5 servers that basically these servers store the same data. And this is your replicated log. Basically a list of operations that each server should apply in the same order. Now imagine that 2 of those servers crash and the remaining actually need to figure out, they need to function correctly and agree on the current state. They cannot just call a meeting or vote. They're basically computers. And they need a protocol that will help them to function. This protocol is basically called consensus algorithm. And before Raft, the only thing on the town was basically called something like Paxos, which is famously, notoriously, legendarily difficult to understand. And the authors of Raft actually say that, by the way, for this video, I used this paper as a reference and I read the paper and basically the authors, they say that they couldn't really understood the Paxos until they had better alternative. So it also took them almost a year to figure out. So we can clearly say that Raft was born out of frustration, and it only exists to do what Paxos does, but in a way that human being can actually follow. And from even the paper, I would like to add this quote that it says that Raft's primary design goal was understandability. Okay, so distributed consensus answers only one question: how a bunch of machines agree on something when any of them might crash or go unreachable at any time. Think of it as a group chat where some people have no signal. They still need the group to make a decision, or they cannot just wait forever for everyone to respond. So basically, Raft gives that. Raft gives you this 3 guarantees. First is the safety. It will never tell you the wrong answer. Second, it's availability. It keeps working as long as majority of servers are alive. And 5 servers means that you can actually lose 2 and still would be fine. Third one is correctness. So it does not really depend on timing. Even like slow networks can just slow and they do not corrupt results. So the real systems you already know, like Zookeeper, Google's Chubby, HDFS, all rely on algorithms like this underneath. But Raft is just a version you can actually read and understand it. Okay, now I would like to move on to the key components sections, and here I will talk about the 3 roles. So basically, Raft simplifies everything by just having a clear hierarchy. At any moment, every server is one of these 3 roles. We have leader. Leader is basically the single boss. Every client request goes through the leader. So it decides the order of operations or tells everyone else what to do. This is basically exactly like there's only one exact leader at a time and no other debates. We also have followers here. Basically, followers are the passive ones. They basically sit there, wait for the instructions from the leader, and then they respond. They do not initiate anything on their own. They basically obey the rules. Candidates are the candidates are basically first followers, and they're just tired of waiting. So if a follower hasn't heard from the leader for a while, and then what Raft calls election timeout. So it assumes that the leader is dead and decides to run for election itself. So it transitions to candidate state, and then, so basically the flow is like this. We have every server in the beginning is a follower, and then some of the followers are turning into candidates, potential leaders, and we have only one leader at a time. And if there's timeout, candidates runs election by themselves. So this is very interesting. So can you think of a real world analogy for this exact situation? Now I would like to actually move into the very interesting part, which is the leader election. So in Raft, like how does a leader actually get selected? So basically Raft uses something beautifully simple, randomness, like basically randomized timer. So every follower has an election timeout, a random value, which is typically between 150 and 300 milliseconds. And if it does not hear from a leader before the timer expires, it assumes the leader is gone, and basically it starts election. You can ask like why randomize? Because if everybody had the same timeout, they'd start an election at exactly the same moment, and no one actually would win. So basically, randomness spreads them out so that no server actually fires first. But the candidate increments, what Raft calls this term, think the term as a logical clock, or let's say election cycle. Vote sits for itself, sends request vote messages to everyone, to every other server. So let's say if it gets votes from the majority, let's say for 5 server, it means 3, it basically wins. It immediately sends heartbeat messages, and it says to the followers that a new leader is elected, basically. Let's say if 2 candidates fire at the same time and split the vote. Basically here in this scenario, they both time out again, pick a new random delay, and try again. Basically, Raft guarantees this whole situation resolve quickly. And this is basically what we call democracy. Now we are moving into the log replication. Basically, once there's a leader, it accepts client requests, and each request is a command. Let's say maybe x equals to 5. Leader appends this message, this command, to its own log, and its log is basically a sequential list of operations, and it sends it to the followers using basically what Raft calls append entries, RPC. And RPCs are basically just messages between servers. Once a majority of servers write the entry to their log and confirm it, the leader basically commits the entry, applies to the state machine, and sends the result back to the client. You may notice that you actually do not need all servers to respond, just the majority. Because let's say some servers, let's say in one server scenario, one server is maybe just slow or temporarily unreachable. So the system always needs to keep moving. The slow server will catch up later. Another important thing is that logs only ever flow in one direction, from leader to followers. There's no negotiation. The leader's log is the only truth, let's say, it's the only ground truth. And another important thing is that the leader append only property. I would like to mention that a leader never overrides or deletes its own log entries. It only always like appends. Talk about committed entries. In Raft, committing an entry is basically the single truth moment in Raft, because before an entry is committed, it's actually provisional, so it may get overwritten if the leader decides or like things go wrong, but it's when it's committed, it's permanent. Raft guarantees that the future leader will also have this information. Even if the current leader crashes, the next leader will have it. And let's say the formal property here, we can call it state machine safety. If any server applies, let's say, comment C at index 5, no other server will apply it different command in index 5. They will basically execute it in the same history, in the same order. just to know that committed means a safe, permanent, agreed upon by everyone who matters, by the majority, let's say.
Now let's see how Raft handles an actual failure scenario. We start with 5 servers. S1 is the leader, and S2 through S5 are followers. Everything is working normally. The leader is replicating log entries and sending heartbeats. Then suddenly S1 crashes. The followers stop receiving heartbeats. After a short timeout, S2 reacts first. It becomes a candidate, starts a new election term, and sends request vote RPCs to the other servers. S3 and S4 grant their votes, giving S2 a majority, 3 out of 5 servers. That officially makes S2 the new leader. As soon as S2 wins, it begins sending heartbeats to the cluster. The election stops, the followers synchronize with the new leader, and normal operation resumes. From the client's perspective, this interruption is very small, usually around one election timeout, roughly 150 to 300 milliseconds. And if the old leader, S1 later comes back online, it sees the newer term number and safely returns as a follower. No split brain situation occurs.
Now I want to quickly wrap up this video. So basically, as you understand from this lecture, that Raft is a consensus algorithm. It's a way of cluster of computers to agree on the same log of operations, even when the servers fail. It does this through it does it on 3 key ideas: one leader at a time, elected by majority of the votes, and a replicated log that flows only from leader to followers. And committed entries are the guaranteed ones to survive any future crash. The whole thing was designed to be understandable, and I hope that today's lecture also showed that show that in this video. That's Raft. Thanks for watching, and remember that in distributed systems, the real enemies are not bugs, they're messages that never arrive.